Right, cut off again. So the incoming wind speed, I stop at there. So the incoming wind speed must be 3 times higher or 3 times faster than the outgoing speed from the wind turbine. So as we substitute V2 over V1 with 1 over 3, and then we simplify this equation, we will obtain this form. And notice that the half rho AV cube over here is the theoretical wind power that can be given to us if we consider a particular amount of wind, which is the wind that gives us the V1, the incoming wind, right? So the theoretical maximum power that the incoming wind can give us is this. This is the maximum power that this is the theoretical power that the incoming wind to the wind turbine that we can extract. But when it goes through the wind turbine and then we extract uh, the power from wind turbine, because that is the only power that we can connect to the grid. We cannot connect the power from the wind, the incoming wind, to the grid. We cannot do that. We can only connect the power that is generated from the wind turbine into the grid. Okay, therefore, we are calculating the extractable power from the wind turbine and not the theoretical power from the incoming wind. And then as we substitute V2 over V1 equals to 1 over 3 over here, and then we simplify this equation, we notice that the maximum extractable power from the wind turbine is only equals to 59.3% of the theoretical wind power that is offered by the incoming wind. And that says a lot, right? And this is an ideal case whereby the wind turbine doesn't experience any losses, such as friction loss, sound loss, or any other inefficiencies in the operations of the wind turbine. So even in an ideal case, the maximum extractable power from the wind turbine is only equals to 59.3% of the total incoming wind power that is offered by the wind. Okay, and this is a very important properties, and this is the equation, the golden equation that wind turbine designers use or refer to when designing their wind turbine. And this is only a table where I have calculated various extractable power based on different wind speed and also different cross-sectional area where the wind is going through, the cross-sectional area being the cross-sectional area of the wind turbine, depending on the length of the blade. Okay. So practical power extractable from the wind. So several comments. The power actually extractable by a wind turbine, okay, is much less than the maximum theoretical value, as we have witnessed just now. It's only equals to 59.3% of the maximum wind power that is offered to us from the incoming wind. A practical wind machine experiences air drag and air frictions on the rotor blade, causing heat losses. In addition, the rotations of the blade causes swirling of the air and eddies, which reduce the torque imparted to the blade. So eddies is the eddies current, and swirling of the air. Yeah? Swirling is like when you experience strong airflow, then the blade will sort of vibrate. Okay, if you can imagine what I'm trying to say, yeah. And that is a form of inefficiency, and that will reduce the outgoing wind speed, and also the power that the efficiency of the rotation. Okay, and the net effect of various losses is normally incorporated into a parameters called power coefficient CP. Okay, this we will see later on. Yeah, and this is what they mean. What they mean, right? So extractable power is equals to, just now what we say, 59.3% of half rho AV cube, and that is the maximum. Okay, that is the maximum power that you can extract. But normally, right? Normally, as I've written here, normally CP is between 0 to 0.4. The maximum you can go is 0.593. And even when we have the maximum CP of 0.4, which is a practical value, okay, a practical value. A practical value is 0.4, the maximum can go is 0.4. The theoretical